How strong electric fields change the chemistry of water. Water seems simple, but inside devices like electrolyzers, where electricity is used to split water, it behaves in surprising ways. New research shows that strong electric fields can completely change the rules that normally control how water molecules break apart. Instead of needing extra energy, water starts splitting because the molecules become more disordered. In other words, chaos, not energy, drives the reaction. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. This discovery also reveals that powerful electric fields can make water far more acidic than usual, a finding that could strongly affect how future hydrogen-producing technologies are designed. Why water splitting matters. Hydrogen is widely considered a clean fuel of the future, and one of the main ways to produce it is by splitting water using electricity, a process called electrolysis. To improve this technology, scientists need to understand exactly how water behaves under electrical conditions. A closely related process, called water autodissociation, happens when water molecules briefly split into charged parts, hydrogen ions and hydroxide ions, even without an external reaction. Under everyday conditions, this happens only rarely, but inside electrochemical devices, water experiences very strong electric fields, and until now, scientists did not fully understand how those fields change water's behavior, energy, disorder, and why reactions happen in nature. Two main factors decide whether a chemical reaction happens on its own. 1. Energy. Systems prefer to move toward lower energy. 2. Disorder. Entropy. Systems also naturally move toward greater disorder. A reaction can proceed if it lowers energy, increases disorder, or does both. In ordinary water, autodissociation is discouraged for both reasons. It costs energy. It reduces disorder, so water molecules usually stay intact. What changes under strong electric fields? Researchers from the Max Planck Institute for Polymer Research and the University of Cambridge discovered something unexpected. When strong electric fields are applied, water behaves in almost the opposite way. Using detailed computer simulations, they found that electric fields first force water molecules into a very orderly arrangement. This artificial order makes the system tense and unstable. When water molecules begin to split into ions, that rigid structure collapses, creating more disorder. That sudden increase in disorder makes the reaction favorable. So instead of energy driving the reaction, the system wants to become more disordered, and that desire pushes water molecules to break apart. As one of the researchers explained, this flips the normal rule. In everyday water, disorder prevents splitting. In strong electric fields, disorder causes splitting. Electric fields can make water acidic. The team also found that intense electric fields can dramatically change water's acidity. Normally, pure water has a neutral pH of 7. Under strong electric fields, the pH can drop to around 3, similar to vinegar. This means that inside electrochemical devices, water may become much more acidic than engineers expect, affecting reaction speeds, material stability, catalyst performance. Why this discovery matters. These findings suggest that many existing models of water chemistry may be incomplete when electric fields are involved. Scientists designing better hydrogen-producing systems will need to consider not just energy, but how electric fields reshape molecular order and disorder. More broadly, this research shows that electric fields can fundamentally rewrite chemical behavior, opening new possibilities for improved electrochemical devices, more efficient catalysts, better control of reactions that happen in water. The big idea in simple terms: normally, water resists breaking apart. Strong electric fields force water into order, and when that order collapses, the resulting chaos drives the reaction forward. It's a powerful reminder that in chemistry, just like in life, sometimes disorder is not a problem, but